Okay, let's dive right into this. Welcome, focused learners, to this high-octane explainer. Today, we are strapping in and navigating the absolute wasteland of tricky Cambridge computer science past paper questions. If you were sitting there preparing to tackle syllabus codes 0417, 0478, 2210, or 9618, you have almost certainly encountered that terrifying moment in an exam. You know the one. You read a question, your mind goes completely blank, the clock is relentlessly ticking down, and you can practically feel the marks just slipping through your fingers into the sand. But fear not, because today I am going to guide you through this treacherous, high-pressure territory to help you claim your ultimate grade treasure. We aren't just going to look at random facts today. We are going to use a notoriously tricky, totally misunderstood topic, sound sampling and resolution, as our core vehicle to decode exactly how examiners think. We're going to get into their heads. By the time we wrap up this explainer, you won't just understand the mechanics of digital sound, you will possess a master key, a strategy that unlocks top marks across your entire computer science paper. So get your notes ready, because this is going to be a game changer.
Here is our survival map for today. First, we'll face the challenge head-on. Then, we move to the strategy reveal, followed by the transformation of an actual answer. After that, we'll put you to the test in our interactive workshop, and finally, we'll lock everything in with the final system.
Let's kick things off with part one, the challenge. To understand how to win this exam game, we first really need to look at how students typically lose. And usually it's by treating computer science like it's just a disconnected vocabulary list.
Now, you might be wondering, why start here? What's really interesting about the question on this screen is how it frames the entire concept. What problem does sound sampling actually solve in a digital device? Top-tier students, the ones securing those A stars, they understand the practical, real-world consequence of a concept long before they ever try to memorize the textbook terminology. So let's break down the core digital problem we are facing. The real world around us, it is analog, it's fluid. Sound waves are completely continuous, flowing seamlessly from one value to the next. But a digital device, whether that's your sleek new smartphone or a basic computer microphone, is essentially just a rock that humanity tricked into thinking using binary, just ones and zeros, absolutely rigid. It literally cannot process a continuous wave. It doesn't understand fluid. Therefore, we are forced to solve this problem by converting that physical, continuous wave into discrete, separate digital values. That is the entire fundamental reason sound sampling exists. It's a bridge between the physical world and the digital brain. When you actually understand the reason for the concept, the terminology just sticks naturally, and you completely avoid the trap of just memorizing isolated, meaningless definitions.
To really see where things go wrong, let's look at two typical students. We'll call them Alex and Sam. They represent the two most common traps I see as an examiner when grading Cambridge papers. Let's look at a real comparison of how they answered a past paper question that simply asked them to explain how a computer records sound. Now, on the left, we have Alex. Alex writes, "Sampling is when a computer measures sound waves to make an audio file." Alex is what I call a memorizer. Alex overloads on raw facts, but provides absolutely zero analysis. This answer feels safe, sure, but it is incredibly shallow. It is a basic description, it is not an explanation. It doesn't tell us how or why. Then, on the right side, we have Sam. Sam reads the word sound, immediately panics, rushes the answer, and writes, "The computer uses high resolution and file compression to send the sound over the network faster so it doesn't lag." Oh, Sam. Sam has completely missed the command word requirements and ignored the context of the question entirely, jumping wildly into file transmission instead of the actual recording process. Both of these students have lost massive marks. Why? Because they don't have a structured approach to decoding the examiner's demand. They're just throwing words at the page and hoping something sticks.
That brings us to part two, the strategy reveal. We are going to look at the exact core strategy used by expert examiners to systematically build a high-scoring answer. And hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's look at the 3 layers of mastery, and we'll use sound sampling as our vehicle to drive through it. This is how you build up your knowledge so it's bulletproof. Layer 1 is everyday language. This is your simple conversational explanation. You might say it's taking rapid snapshots of a sound wave. Now that is fantastic for your own internal understanding. It makes sense to your brain. But let's be real, it is not going to score you marks on a Cambridge exam. So we must climb to layer 2, technical vocabulary. We upgrade our phrasing. We might say, measuring the amplitude of a wave at regular time intervals. Okay, much better. We are using the right words now, but it's still not a fully fleshed out top-tier answer. It lacks the structure required by the assessment objectives. That's why we must reach layer 3, the exam explanation. This is where we shape the idea into a response that actually scores maximum marks under intense time pressure, often utilizing the Peel framework, point, evidence, explanation, link. A layer 3 answer looks like this. The continuous analog wave is converted to discrete digital values by an analog to digital converter, which samples the amplitude at a set rate. A higher sample resolution allocates more bits per sample, increasing accuracy but also proportionally increasing file size. Boom. That is exactly how you ascend from basic understanding to an A-star performance.
So the absolute most crucial point here is understanding the boundary between command words. This is where the Peel framework really starts to shine. A massive point of failure for students is not separating a description from an explanation. If a Cambridge exam asks you to describe, they just want to know what the device, process, or method actually is. You identify the points. But, and this is a huge but, if they ask you to explain, they want to know how it works and why it matters in that specific context. You need the explanation and link parts of Peel. If you only describe when you're explicitly asked to explain, your answer sounds incomplete to the examiner. You're leaving points on the table. Conversely, if you jump straight into explaining the complex mechanics without first clearly naming and defining the concept, your answer just sounds confused and disorganized. You have to decode the command word first, every single time.
Let's move into part 3, the transformation. It's time to introduce the disciplined step-by-step teacher walkthrough path that will transform those flawed, panicked answers into sheer perfection.
Let me break down this 4-step computer science success blueprint for answering these tricky questions. You need to memorize this sequence. Step 1, identify the demand. Look immediately at the command word. Is the examiner testing process explanation? Are they testing hardware selection or maybe logic reasoning? Know your battle before you fight it. Step 2, classify the concept. Are we talking about sample rate, which is about time, or are we talking about sample resolution, which is about detail? Do not mix these up. They are totally different things. Step 3, sequence step by step. Clarity of sequence matters immensely in computer science. Don't jump forwards and backwards like you're time traveling. Order your steps logically from the analog input all the way through to the digital output. Finally, step 4, connect to context. Generic copy-pasted textbook responses rarely gain full marks. A highly logical sequence that is specifically tailored to the scenario in the prompt is vastly superior to just vomiting facts in a random order.
Now, pay close attention because what's really interesting about this next slide is watching the transformation happen live. Imagine I am holding the examiner's red pen right now. On the left side, we have an unformatted typical student answer. Resolution makes sound better by using more bits so the file is bigger. I see this all the time. It has zero flow, it is missing key technical details, and it's barely going to scrape a single mark. Now, look at the right side. We take those same basic ideas, but we apply our structured blueprint using the Peel framework I mentioned earlier. First, the point. We define it clearly. Sample resolution is the number of bits assigned to each individual sample. Bang, 1 mark. Next, the evidence and explanation. We explain how it works. By allocating more bits, such as moving from an 8-bit depth to a 16-bit depth, the computer can record a much wider range of amplitudes. That is clear mechanical explanation. Another mark. Finally, the link. We connect it back to the consequence. This results in a far more accurate digital representation of the original analog wave, though it proportionally increases the final storage size of the file. Do you see the difference? Every single structural change secures an additional mark. It defines the concept, it explains the underlying mechanism, and it explicitly states the consequence. That is how you guarantee marks.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, welcome back. We are jumping right into part 4, the interactive workshop. Remember, generic answers put a hard cap on your grade. Let's test your ability to actually apply context under pressure. We are going to do a data scan challenge. Imagine I'm putting a 60-second virtual timer on the clock right now. Picture this. You turn the page of your exam, and you are faced with a highly complex data table. It shows a mobile phone streaming live audio over a very weak, struggling 3G network. The data source shows various different sample rates and bit depths on one axis and buffer lag times on the other. Your challenge in those first 60 seconds is to mentally extract the core data trend. The clock is ticking in your head. What is the examiner actually trying to test here with all this noise? I'll tell you. They aren't just testing if you can recite the definition of resolution. Anyone can do that. They are testing your ability to look at that chart and logically deduce that higher sample rates and higher resolutions create vastly larger file sizes. And why does that matter? Because those massive file sizes directly cause higher latency and buffering on a bandwidth-constrained mobile network. If you just write down the definition of sampling here, you get absolutely 0 marks. You must extract the trend from the data and directly connect the theoretical computer science concept, file size, to the practical real-world scenario, network lag. Okay, how would you have done on that? Now for our next challenge, I want you to find the flaw. Let's look at the most common flaws examiners see repeatedly, paper after paper. I'm going to fire these off, and I want you to think about if you've ever made these mistakes. Flaw number 1, vague wording. This is a killer. Writing something like, "it makes the sound better," instead of the precise technical phrase, "it increases the accuracy of the digitized wave." Better is not a computer science term. Flaw number 2, confusing similar terms. Mixing up sample rate, which is how often we take a measurement, with sample resolution, which is how much detail is in each individual measurement. They are two sides of the same coin, but totally distinct. Flaw number 3, missing steps in a process. This happens when students rush, like completely forgetting to mention that the analog to digital converter, the ADC, is actually the piece of hardware doing the work. You can't just say the computer does it. And finally, flaw number 4, ignoring context, exactly like we just discussed in the mobile phone scenario. If you state a brilliant technical advantage but give no reason, or if you identify a piece of hardware but completely fail to justify its use in the specific scenario given in the prompt, you were just leaving easy marks sitting on the table. In our speed writing workshops, we give students 30 seconds to write one perfect Peel paragraph to iron out exactly these flaws.
We have arrived at part 5, the final system. Let's consolidate everything we've talked about into one cohesive, foolproof framework that you can use the night before any exam to guarantee top marks. I want you to treat this as your ultimate self-check. If you are sitting at your desk reviewing your notes on sound sampling, or honestly, any other computer science topic on the syllabus, I want you to ask yourself these 4 specific questions aloud. Question 1, what is it? Can you define it clearly without looking at the book? Question 2, how does it work? Can you explain the actual sequence or mechanical process step by step? Question 3, where is it used? Can you provide a realistic, real-world scenario where this technology makes sense? And question 4, why is it better or worse? Can you evaluate it against alternatives? For example, evaluating the trade-offs of high resolution versus low resolution. Listen to me on this. If you can answer all 4 of these questions confidently, out loud, to an empty room, then your knowledge is officially examination ready. You have mastered it. But if you hesitate, if you stumble on question 2 or 3, that tells you exactly where your blind spot is. It means you need another cycle of reading and active recall. It's a binary system. It's really that simple. And this brings us to a really beautiful quote and a core philosophy of our entire study method here. Real-world transfer converts memory into usefulness. Think about what that actually means. When you take the time to connect highly abstract concepts, like discrete digital sampling, to familiar everyday technology, the magic happens. Think about the voice recognition software in your phone, or the automated audio sensors in a smart home, or how robotics process environmental sounds. When you make those connections, the knowledge sticks permanently in your brain. You finally stop just remembering a label from a textbook, and you start remembering the fundamental, logical reason that the concept exists in our world at all. That depth of understanding, that ability to transfer knowledge to new contexts, is exactly what the Cambridge examiners are desperately looking to reward with top marks. We see the results of this method all the time. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder: subscribe to our YouTube channel AC Exams at acexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here. Keep analyzing, keep structuring your answers, and I'll see you in the next explainer.